So in this video I am going to explain the penalty approach method to solve the FEM problems. Okay, so by using the one example we'll try to understand the penalty approach, and also we'll calculate the nodal displacement by using the boundary conditions. And so here is the given problem having three elements. This is element 1, element 2 and element 3, and both their ends are fixed. Okay, both their ends are fixed and the load is applied at this point. The direction is toward the right. Let us say that load is P. Okay, and the different values for the given problems are, for example, the length for the element 1 is 200, and for element 2 300, and for element 3 again it's 200, and area for this element 1, let us say A1, 2400 millimeter square, and for element 2 it is 600, and for element 3 again it's 2400 millimeter square. And Young's modulus value for element 1 it is 70 into 10 power of 9 Newton per meter square, and for element 2 say E1 and this is E2, it is given as 200 into 10 power of 9 Newton meter square, Newton per meter square. Okay, and the value of P I will write here. It is given 200 into 10 power of 3 Newton. So here first we have to check whether all the dimensions are in the standard format. For example, the length are given in millimeter and area is also 2400 millimeter square, and where Young's modulus it is given as in Newton meter square, Newton per meter square. So you have to convert into Newton per millimeter square so that all the values will be in the standard format like in millimeter. So now 70 into 10 power of 3 Newton per millimeter square if you convert it, and here also same thing, 200 into 10 power of 3 Newton per millimeter square. So these are the basics we already learned earlier. Now as the procedure will start normally as you have done in the elimination method, also same thing you have to use. Okay, so in the elimination method also we have calculated the element stiffness matrix, then we have made the global stiffness matrix. Okay, then after that, after the global stiffness matrix only there will be changes for the penalty approaches. Okay, the steps it will be followed by the penalty approach after the global stiffness matrix only. Till then the procedure it will be same. Okay, so now you can calculate K1. K1 is what? It is the element stiffness matrix for element 1. Okay, so K1 is equal to, it will be E1 by L1 in bracket there will be K1 minus 1 minus 1 minus 1 1. So before that we will calculate the matrix like common matrix K1 minus K1 minus K1 K1, and for K2 is K2 minus K2 minus K2 plus K2. Okay, so for K3 we can modify one thing, because here the area is same for both the element 1 and 3, and also the length, both the elements are same. It means we can say that where for element 1 and element 3 both are equal, and also their material property E1 is also same as E3. Okay, because it's not mentioned in the question, so that we can take E1 is equal to E3, or sometimes it will be mentioned in the question itself. Okay, because E1 and E2 only it is mentioned, so I can take E1 as is equal to E3. Okay, so after that we will calculate the value of K. So with K is equal to small is equal to K1 is equal to, it is A1 E1 by L1. Okay, 1 1 1. So A value, that is 2400, into E value for the element 1 70 into 10 power of 3 now, divided by length for the element 1, that is given 200. So from this calculation got 84 into 10 power of 4, okay, Newton millimeter. So this is as equal to K3 value. Now you need to calculate the value for K2. Again A2 E2 by L2. So A2 value is given 600 into E2 value, that is 200 into 10 power of 3 divided by 300. Okay, so from this calculation we got 40 into 10 power of 4. Okay, this is the value of K2, K1, K3, and this is K2. Okay, now we'll go for calculating the global stiffness matrix. So adding all the stiffness matrix, where capital K is equal to K1 plus K2 plus K3. Okay, so for that we'll make a general formation, like here it will be K1 if we use the global stiffness matrix. So K1 minus K1, then 0, next minus K1, so here it will be K1 plus K2, now again 0, in the third row 0 minus K2, so there will be 4 row, yes, K1 minus K1 0 0, and K1 plus K2, here there will be K2 value, okay, this is minus K2 because it's in symmetry, again 0. So for third row third column, again it is K2 plus K3, so K3 is equal to again as K1 minus K1, fourth. So 0 0 minus K1, here K3, so that is equal to K1 you can write. Okay, so this is becomes an global stiffness matrix. Now we'll substitute the value. See, in all the matrix 10 power of 4 is common, even in K1 K2 K3 also. So we'll take 10 power of 4 is common outside the matrix. Then in the matrix, now K1 value which we got, that is 84, and K2 is, so 84 will be minus 84, 0 0 minus 84, and K1 plus K2, it means 84 plus 40, it is 124, yeah, 124. Now minus K2 value is 40, again 0 0 minus 40, So here K2, K3. So K2 again 124 only will get. So minus K1 value 40. No, 84. 0 0 minus 84 minus K1, again K1 value, that is 84 only. So this becomes a global stiffness matrix. Okay, similarly we'll calculate the displacement vector. So anyhow displacement vector it will be u1, u2, u3, u4, and force vector it will be changed because the force is applied at node 2. So finally I will write in the finite element equation. So that is finite element equation is what, where F is equal to Ku is equal to F, right? So in this format I will write, and some unknown value also directly I can add in the equation itself to avoid the steps. Okay, so first row there will be 84 minus 84 0 0. Second row minus 84 124 minus 40 0 0 minus 40 again 124 minus 84. So here minus 84 plus 84 0 0. So this becomes K value. Now similarly we'll write U value. U is the unknown displacement, like U1, U2, U3, U4 is equal to F1. Okay, so where F1 there is no force applied, so you can write 0. Now F2 the force is applied at node 2, that is 200 into 10 power of 3 is given. Okay, so 200 into 10 power of 3, and what is the, we'll write 200 into 10 power of, means it is 2 into 10 power of 5, we can directly write again 0 0. Okay, and one more thing here, for this globeness matrix 10 power of 4 is outside matrix, so we forget to 4. Okay, now there is a, now we can go for applying the penalty approach. Here the procedure will start, even for the elimination method and also for the penalty approach. Till now the procedure will be same. Okay, so in the penalty approach, in this row, okay, so in the diagonal we have to find which is the maximum value in this diagonal, because the maximum value generally we can find in the diagonal itself. So where 124 is the maximum value in the diagonal, both values are same, so 124 is the maximum. So we can write the C indicates maximum of Kij into 10 power of 4 is the standard format. So now we can take max value is 124 into 10 power of 4 is the maximum stiffness in this problem. Okay, so after that we can again modify it in the row 1 and also in the row 4, because in the row 4 row 1 is also fixed and row 4 is also fixed. To make the equilibrium of balancing the problem, we have to add the maximum stiffness in the equation 1 and also in the equation 4 here and here. Okay, so that we'll make what it as
this in the equation. For example, like U1, it will be your getting 0. Okay, like that, the remaining values you need to calculate as like our previous cases, how we have calculated in the elimination method, same you need to follow. Okay, and also sometimes you need to calculate the reaction forces and also stresses in the elements. Okay, that you have to follow. Only this I want to say, you can add the penalty approach method when if you want to solve the any type of element problems. Thank you.